senior visitors to Berkeley. The more recent innovation has been to run things through the summer. We currently have our first summer program running on foundations of deep learning. And the other thing we've been doing is run these summer clusters, so smaller activities that we can organize on a shorter time scale for things that are fast-moving or more speculative, or just better suited to run something perhaps more narrowly focused than a full program. We've only run a few of these, but so far they seem to be really successful. And the bootcamp today is part of the summer cluster on error correcting codes and high-dimensional expansion, which starts today. So welcome to that. The goals of the bootcamps are intended to be a kind of scientific and social icebreaker for the cluster, getting everyone on the same page technically. But also they have a kind of archival educational purpose, kind of recording the state of the art in a particular field, because the videos of the talks go online. I'm sure you've all seen our website. They're amazingly popular for the kind of technical levels of the content. I think we passed 2 million views pretty recently, which is impressive. So this cluster is supported by the Patrick J. McGovern Foundation, so thanks to them for that. A big thank you to the organisers of the bootcamp, Irit and Prahladh, who are also the organisers of the cluster, so thanks to them for all of that. And as you can see, Prahladh can't be here today. He's held up with visa issues, unfortunately. We're hoping they'll get resolved really soon. So I'll hand over to Irit in just one moment. I want to say a few words about logistics. We try to keep the Institute, and in particular these meeting rooms, in good shape, so we ask that you don't bring tea and coffee and food in here. Water is fine, but leave those other things outside. For the morning and afternoon breaks, we've got tea, coffee and snacks out here. For lunches you're on your own, and today it is particularly long and hopefully very social lunch break. I guess Irit's going to say a little more about the changes to the schedule. If you want to keep things in lockers in the hallway on the far side of the ground floor here, you'll find lockers that you can use with a PIN code. For wireless access, you've probably already discovered Cal Visitor works for everybody, and if you authenticate using EduRoam with your home institution, you can use that too. As I say, our talks are live streamed and archived on our YouTube channel and our website. And Darren, the videographer here, is going to be helping the speakers connect up. So talk to him about that. And also a big thank you to the events coordinators. So Tom Thompson is over here, but also Kamal Walji and Kevin Hung put a lot of effort into the local organisation to make the bootcamp happen. So big thanks to them. And if you have questions, logistics sorts of questions, you can direct them to Tom, Kamal or Kevin. All right, thanks a lot. So you read.
Hi everyone, and welcome. So happy to see everyone, and finally...
Louder.
Welcome everyone. It's great to see you. And we're going to start the boot camp now. As you've seen, Prahladh unfortunately wasn't able to get a visa, and so this is going to cause a bit of a schedule change because because of the time difference, having him talk later in the day is going to be really late at night for him. So tomorrow, the other talk he was going to give today will be postponed till tomorrow. Tomorrow he will give 2 hours in the morning, and you can look online for the remaining schedule change. Tomorrow is going to be a slightly longer day. And today we will, instead of his talk, we will shift things up, and Uptown will talk 3 to 4, and then the reception will be at 4 today. Okay, so before we begin, I just want to thank Peter and the Simons Institute for hosting us. It's such a beautiful place. I'm so happy to be here. And also thanks for all the last-minute changes. It was not so trivial to get this arranged, so thanks a lot. Now I don't see what Peter went, but let's start.
Hi everybody.
Can you hear me? Or
Oh, one more thing I forgot that Prahladh asked. He can only see the middle part of the audience, so if you want to ask a question, just come to the middle aisle to ask. You can stay.
So basically, I can see all the way from Yuval over there to, I don't know the left, rightmost. Two people to the left of Madhur.
Okay.
To the right of Madhur, sorry.
You can see almost everyone then.
Yeah. Okay. Very good morning to all of you. It's not that good morning. For me, it's about 10 p.m. here in Bombay, being battered by the Indian monsoon outside. I was hoping to be there, but the US Mumbai consulate decided otherwise, and my visa has been held for some administrative processing, and hopefully I should get it in a couple of days, and I'll join you guys next week if everything works out well. Yeah, and so as I mentioned, because there's a slight change, thanks to Simons for accommodating this last minute. So I will be giving all my talks remotely, and you don't want to be seeing me give the talk at 4 a.m. in the morning, both you and me. So all my afternoon talks have been moved to tomorrow, and there's going to be a schedule change announced. Anyway, so much for that. Let's get started. Let's go to the main topic of the day. So what I plan to do, feel free to, this is going to be introductory talk. So I don't have to cover all the material that I plan to do. So feel free to interrupt me with questions and response. When I did the test run, I could hear people from all around the room, though I can't see everybody. So feel free to stop me as and when. I have a sort of a whiteboard here too, in which I can write and answer questions as we keep going along. Okay, so what I plan to do in this introductory talk is sort of give my motivations, or sort of why towards working in this area, high-dimensional expanders, for the last 2 years. I've been working in this area for the last 3 to 4 years, and I would like to give you what's the motivation behind it. So the math community and the combinatorics community have been working on it for much, much longer. The TCS community has got interested the last 4 or 5 years, and right, the high-dimensional expanders, just like the word expanders, does not refer to a single object. It refers to a class of similar objects. And what we will see over the course of the bootcamp is various objects of this flavor. I'll be talking about a particular type of high-dimensional expanders. I'll introduce that during my talk. Yotam and Irit will do another but equivalent one in their talks, and Yuli will be giving some more other notions of high-dimensional expanders in his talk tomorrow. So in fact, the way my talk is going to be structured is, for the most part of the talk, I'm going to talk about motivations and applications, and I'll actually come to the main, what a high-dimensional expander is, at the very end of the talk. I'll introduce it. I'll sort of motivate why we care about such an object, even without defining this object, and we'll come to the actual definition possibly at the very end of the talk. In some sense, you'll be hearing the story from me, in which I will be delaying the main character or the protagonist till the very end of the. So, I don't know if my slides work. So, as I had mentioned in my abstract, the sort of 3 things which I would like to sort of concentrate in this talk is trying to ask, what are these objects which are called high-dimensional expanders? Are there sparse versions of these objects? And why, and are these objects interesting and useful? In fact, I'll try to answer these 3 questions in the reverse order. So I'll start off, after having set the stage and enough notation, we'll start off with an application, and a very compelling application in my viewpoint, and see why, when we talk about this application, some sort of expanding object in a large dimension and a sparse version of this object will be very useful for us. And while trying to understand more after this, we'll eventually stumble on the definition, and that will be the way the talk is going to be structured. So let's get started. So let's start off with some of the objects which we are very familiar with, the classical notion of expander graphs. So what are expander graphs? Informally speaking, they are these magical graphs in which every not too large set expands. This is what an expander graph is. And there are various ways to formalize this notion. One concrete combinatorial way of formalizing this is the notion of vertex expansion, which states that take any set of vertices which is not too large and the neighborhood of this set is reasonably large. That's vertex expansion. One could also define what's called edge expansion, in which you take any set of vertices, and if you look at, which is not too large once again, and if you look at the number of edges leaving this set compared to the number of edges that could be leaving this set, if you look at this fraction, this is a reasonable quantity. This is what is called edge expansion. These are two combinatorial notions of expansion. Then we have the spectral notion of expansion, in which if you look at the second eigenvalue of the normalized adjacency matrix, or actually the maximum of the second eigenvalue and the least eigenvalue, the absolute value of the least eigenvalue, and this eigenvalue is bounded away from 1. This is what's called spectral expansion of a graph. An equivalent definition is in terms of random walk, in which one could consider two types of random walks on the graph. The first random walk is you start from a vertex and move to an arbitrary, uniformly chosen random vertex in the graph. This is just ignoring the structure of the graph, you just move to a random vertex. That's random walk 1. And random walk 2 is you're at any vertex and you move to a random neighbor of this vertex, specified by the edges of this graph. This is random walk 2. And if you look at these, and the random walk notion of expander says that if you look at these two, the corresponding transition matrices, you look at them as operators, the spectral norm of the difference between these two operators is small, is bounded by some small constant, say lambda. This is equivalent to the previous notion of spectral expansion. Formally, what I've written here exactly is this: the J times 1 over n refers to the transition matrix corresponding to the random walk in which you move to a completely random vertex. A refers to the random walk in which you move to a random neighbor. And what I've written over here is, if you look at the difference of the spectral norm of the difference between these two operators, that's at most lambda. This is equivalent to the spectral expansion. It's good to keep this random walk expander in mind, because this is something which we will come to towards the end of the talk. These are myriad definitions of expanders, not necessarily all equivalent, but they are, for the large part, they are morally equivalent. You can move from one definition of expander to another definition of expander for most practical purposes. These are not exactly equivalent, this one. And this is the nice thing about expanders and graphs, that is, you have these zillion different notions and they all are sort of equivalent in some way. They arise in different, depending on the application, they arise in different contexts, but yet there are these equivalent, they are morally equivalent, and sort of they have this very rich theory behind them. And of course, you have to head all of this. This is what I said, these are expanders, but the question is, do there exist expanders? Of course, an easy thing to check is all these definitions are satisfied by the complete graph. The complete graph is a great expander in all these definitions. But that's not the main thing. The key thing about expanders is the following theorem, that there exist actually constant degree expander graphs. Graphs which are very, very far from being complete. That is, they have very few edges. The number of edges is only linear in the number of vertices, unlike the complete graph, which is quadratic, and yet they have these amazing properties of expansion. This is the most useful sort of theorem that, with respect to expander graphs, that they exist such sort of expander graphs. And they not just exist, they exist abundantly. A random constant degree graph is an expander graph. And not just a random one, you can actually be, today we all know how to construct them explicitly, super explicitly, and these fact that we know how to do these have various applications for us. For instance, these objects where the notion of expanders was first studied by Barsdin and Kolmogorov while trying to understand neural networks, and Pinsker while trying to understand telephone networks. I think, in fact, the name expander graphs is due to Pinsker. He called it expanding graphs in his paper. So the fact that such explicit objects exist are useful in theoretical computer science. Basically, they were originally used to sort of construct time-space trade-offs. They were used as a possibility for circuit lower bounds. They're used in de-randomization heavily. They're used in metric embeddings. And if I used in Dinu's proof of the PCP theorem, this gives you an alternate proof of the PCP theorem. And more useful for us, they have myriad applications in coding theory. In fact, let's go into some of these applications in coding theory. So coding theory, for instance, we know one, it's an easy consequence of the fact that expanders exist. Actually, here in this case, I'm talking about bipartite expanders. The fact that bipartite expanders exist will immediately give rise to constant rate linear distance codes over the binary alphabet. The other way to get this is by constructing codes over a large alphabet, concatenation, and this gives you a straightforward way to do this. Then you also have the fact that expanders exist lets you to do distance amplification in codes. It lets you take codes from a small distance, construct codes from of large distance. It lets you do this. This is a classical construction of Alone, Brook, Nauer, and Roth. These are combinatorial applications of expander codes. We also have algorithmic applications. In fact, we don't know how to do these anywhere else. Otherwise, we know how to construct codes which are linear time decodable. And only expander-based codes have these properties. And building on this work, this is the work of Supsa and Spielman. Building on this work, Guruswamy and Indick, a decade later, showed that not only do you have linear time unique decodable codes, you also have linear time list decodable codes. And so we have this rich theory in error correcting codes because of the fact that there exist constant degree expander codes which we can explicitly construct. Given this, so what's going to be the question is, do these objects, these expander graphs which have had these magical properties for us so far, do they have analogs in higher dimensions? That's the question which this whole program is going to study. Do they have expansion? What do I mean by higher dimensions? Possibly expansion in hypergraphs. Can we define a new similar theory of expansion in hypergraphs and ask what is it? And of course one can do this, and there are several ways to do this. You could take each of the definitions I have mentioned or any other definition of expanders in the usual graph case and sort of generalize them to the hypergraph case and find out what consequences do these generalizations have, and if we can sort of construct, if these generalizations, or if we can construct objects which satisfy that corresponding generalization, and if we can also use them for some applications. Do these also have? This is one way of doing it. Other way is find out if there is a compelling application and figure out if they need some expanding object or not. So both these directions have been, all these directions have been sort of studied. This is still a burgeoning field. We don't yet fully understand what expansion is in hypergraphs. Unlike the case of graphs in which there are these different definitions, but they are all morally equivalent, each sort of definition.
Have voice messages waiting.
Sorry. There are these multiple definitions, and it's unclear whether these are equivalent definitions or what. So let's actually figure out. So I'll try to talk about one or two attempts, one or two approaches to these, trying to extend the notion of expansion to higher dimensions. So one such approach is the sort of extending the Laplacian, which is to higher dimensions. So what's the Laplacian? So I didn't mention this. This refers to the Cheeger's inequality. The Laplacian comes and trying to study the Cheeger's inequality. This one. For any graph, the G, let's look at the regular graph. For any graph G, we can talk about the Laplacian is a natural quadratic form that is associated with this graph, which is basically this sort of potential function. If you give me any vector x in n dimension, n is the number of vertices, there's a quadratic form associated. The Laplacian maps this vector to a real number defined as follows. It's basically it's a sum of squares over the edges of the difference of the magnitude of x, of the square of the difference of the magnitude of x across the value of the edges. So it's basically Lg of x is summation over the edges of xu minus xv the whole square. So this is what's done in a graph, and this is a very useful object while studying expansion in graphs. This definition of Laplacian has been extended to hypergraphs due to works by Lewis, Soma Yoshida, very recently, actually just earlier this year, in which they show that for a k-uniform hypergraph, now we are moving from graphs to hypergraphs. So the number of vertices per edge is possibly more. If k is sort of 3 or 4 or larger, you can define this notion of Laplacian of hx, which is exactly as above. You sum over all the edges, and you take the difference between the largest value, you take the square of the largest x value and the smallest x value in this edge, and take the square of this. This is a definition. It's not, it doesn't, doesn't come equipped with all the nice linear algebra that came with the previous quadratic form. This is a natural definition, and what these works actually show is you can talk about spectral sparsification. According to this, you can come up with sparser graphs which have the same Laplacians, and there's been a fairly rich amount of work trying to work with this Laplacian. This is one way of trying to extend the definition. What we will do is actually a different this one, which is now begun to take name called high dimensional expanders. And this name comes related to the work from math. In fact, the early definitions of lineal, Mechelin, Gromov, and they have all these various definitions of expanders called topological expanders, cohomological expanders, coboundary expanders. We will see some of these in Uli's talk later tomorrow. But what we'll see in this talk and actually in various talks later today are an extension of the spectral definitions that I talked about. We'll talk about spectral high-dimensional expanders. In fact, we'll see two definitions, the link expanders and random walk expanders. These will be two extensions of two of the definitions I gave earlier, and this is what we will try to work with. Once again, so I won't go into what these definitions are. I'm going to defer this definition till the very end. So before we define it, so what I want to ask is, however we define expanders, one odd thing which we wanted, at least for the graph case, we wanted the complete graph to be an excellent expander. It was the gold standard for expansion. That's how we define. Whatever notion of expander we define, the complete graph was the prototype example for an expanding graph. And then there were these sparser objects which also had these properties and which sort of could be used in lieu of the complete graph. So similarly, if you're going to be working with hypergraphs, what's the gold standard? The gold standard for us should be a complete K-uniform hypergraph. The hypergraph which contains every possible hyperedge of size K. This should be the gold standard. It should be the prototype. Whatever definition of high-dimensional expansion we're going to give, this should be a high-dimensional expander. And then we're going to ask, we're going to come up with some property that this graph satisfies and see if there are sparser the graphs also which have satisfied the same property. This is how we're going to come up with this definition for HDXs. In particular, we're going to ask, what is the high-dimensional property does the complete K-uniform hypergraph need to satisfy to qualify as a HDX? And once we give this property, are there even sparser graphs that satisfy the same property? This is going to be, we want to understand this question. So we want to understand for a large part of the initial talk, we'll try to understand the properties of the complete K-uniform hypergraph and try to find out what, and we'll look at one particular application which will motivate what is this expanding property of the complete K-uniform hypergraph that we are interested in. So when studying K-uniform hypergraph, so natural thing to talk about is the random walk that sort of one can associate with the complete K-uniform. By the way, it's very, very quiet here. Because I can't. So feel free to stop and ask me questions. Because as such, I feel very far away, both distance, and it's very, very quiet. Anyway.
But it's all clear, so
don't worry, don't worry.
Okay. So we're going to talk about. Where was I? So we're going to understand the complete K-uniform hypergraph. Let's look at it from a random walk point of view. We can talk of what's the random walk induced on the 8 vertices of the complete uniform. This is more or less the standard complete graph, and it's not a very interesting object. So let's look at another random walk, which is a random walk on the edges of the complete K. You want to move from one hyperedge to another hyperedge. Now, there are several ways to move across this. One way which we could move is you move from one hyperedge to another hyperedge if they sort of agree on, say, L vertices. This is one way you could potentially move. And so these are the sort of things which you naturally study when you try to understand the random walks on the complete K-uniform hypergraph. And almost immediately once we study this, we will encounter what are called these Johnson graphs. What are Johnson graphs? Johnson graphs are these objects in which the vertices are exactly the hyperedges of the K-uniform complete graph that we talked about. Every vertex, its set of vertices are all the K-sets of the universe of size n, and its edges are exactly those pair of K-sets which have a specified specific intersection, an a priori specific intersection, say L in this case. So if that was the L parameter which we talked about for the random walk, this is the corresponding Johnson graph. We are interested in this is the Johnson graph we are talking about, and we are talking about the random walk in this particular graph. So this is the graph that naturally comes about when we try to talk about random walks in the random walk on the edges of the K-uniform hypergraph. So this is Johnson graph, Johnson graph is a very well studied object. In fact, when you study these Johnson graphs, you'll see that even though I specified it for a particular L, there's a family of Johnson graphs. Once you fix N and K, there is a different Johnson graph for every L, depending on the intersection size. Notice that actually, once you study these graphs, once you try to understand the eigenspectrum of these graphs, notice that you actually have to look at all the L's in this one. There's sort of you can't look at just, when you want to even study one particular L, the Johnson graphs corresponding to the other L automatically pop out. In fact, it's easy to see once you actually do the calculations that for a fixed N and K, as you vary L, all of the corresponding Johnson graphs share the same eigenspectrum. So in other words, it's useful to actually look at these graphs for all L simultaneously in this one, and this sort of will lead us, while studying these hypergraphs, to the simplicial viewpoint of the hypergraph. So what do I mean by that? So this is sort of going to what I'm going to talk about, the simplicial view of every hypergraph. So let's actually first talk about the simplicial view of graphs. So given any graph, given any simple graph with a set of vertices and a set of edge, it's very natural to associate a bipartite graph with this graph, with this particular graph. The bipartite graph is just, you have the set of vertices on one side and the set of edges on the other side, and a vertex and edge are connected if the edge is incident on that particular vertex. So there's a very natural bipartite graph. For perverse reasons, we'll add yet another layer to this graph, which has just the empty set, and connect the empty set to all the vertices. So the reason I'm going to be doing it is we're going to view this three-layered graph as the first layer having all sets of size 0, then the next layer having all sets of size 1, and the third layer having all sets of size 2, which is a set of edges. So you have the empty set, the vertices, and the edges, and this graph is sort of down-closed. That is, once you have an edge, you have all the vertices that participate in the edge, and so on. So this is going to be the simplicial viewpoint of a graph. Given a graph, we're going to view it this way. So the graph is going to be specified. We're going to specify a graph as these three elements. It's the first layer which contains the empty set, the second layer which contains all vertices, and the third layer which contains all edges in the graph. Of course, when viewed this way, the complete graph is exactly the one in which V is the M and E is all pairs of this one. Once I do it this way, it's clear what I should do for a complete K uniform. What's the corresponding simplicial object for the complete K uniform hypergraph? We're going to take a layer which corresponds to all the K sets that participate in the hypergraph, in the K uniform hypergraph, and then down close it. We're going to construct all layers below, which just consists of all potential subsets of this in the most natural sense. So let's define what a simplicial complex is. A simplicial complex is just a collection of subsets of a universe of size n, with the fact that it is subset closed. In other words, if a subset belongs to this class, and if a subset A belongs to this class, and then there's another subset B which is a subset of A, then B should also belong to this class. So this is just for down closing it, and that was the reason for adding the empty set in this one. This is what a simplicial complex is, and we'll sort of identify the layers, each layer by the size of the set that contains it. So the last layer will refer to the actual edges in the hypergraph. The layers below will contain subsets of them. So xi will refer, for historical reasons, xi will refer to all sets which have I plus 1, sizes of I plus 1. And the dimension of the entire complex will be the maximum I for which xi is non-empty. So in particular, for instance, the for the K-uniform complete hypergraph is exactly the set of subsets, the set of all subsets of size at most k, and it is a simplicial complex with dimension k minus 1 lesser, and we will refer to this as the complete complex. So I will call it the K-uniform complete hypergraph, and the complete complex will more or less be synonymous objects to us from now onwards. And just a little more notation before I get to this one. So we'll call a simplicial complex, see the notice the way I've said, need not be defined only by faces of the max dimension. It could be defined by any set of faces, any set of sets, and then just down close it. But we'll call it to be pure if it's defined by faces of just the largest dimension. And notice that once we said this, K-uniform hypergraphs are exactly pure simplicial complexes. These are exactly one and the same object. So we'll move from K-uniform hypergraphs to pure simplicial complexes back and forth. Just notation, I would need one more notation to talk about what I'm going to be doing later. So we will also equip this object. So we have this simplicial complex, which is this K-layered object, rather K+1 layered object. We're going to equip it with one more. This one, we're going to equip it with a distribution on the last layer. Say, let's call it the distribution pi k minus 1. This will in turn induce a distribution on all the layers below in a very natural way. That is, you pick a vertex in the top layer according to the distribution pi k minus 1, and then remove a random element, a uniformly random element from it. That gives you the distribution pi k minus 2. Remove one more element, you get an element distributed according to pi k minus 3, and so on. So this is going to have sort of a joint distribution on all the layers by this simple process. So for instance, if you had worked with the complete K-uniform hypergraph, the natural distribution that one would associate is the uniform distribution on the last layer, which would in turn induce uniform distribution on the respective lower layers also. This need not be the case for any other K-uniform hypergraph. The last, even if you put the uniform distribution on the last layer, if certain regularity conditions are not satisfied, the corresponding distributions in the lower layers might not be uniform. But we will have these distributions in mind. So once again, so this is so much for a lot of setting up of the stage of what I mean by K-uniform hypergraphs. We just moved from the language of K-uniform hypergraphs to simplicial complexes, like pure simplicial complexes of dimension k minus 1. So we will restate our question. What do we do? The question was, again, what is this high dimensional property that the complete complex have to satisfy in order to qualify as a HDX? And then, are there sparser versions of the complete complex that also satisfy the above property? So that's going to be what we want to understand. One. And the way we'll do it is we'll motivate it via an application, and I'll motivate it via an application which is close to my area of research, my home. It will something to do with probabilistically checkable proofs. I'll sort of say so somehow these objects very naturally arise in this context, and there we would be caring about some sort of sparse versions of expanding objects in high dimensions. So what are probabilistically checkable proofs? So let's take a small diversion, come talk about these objects, talk about a few objects that related to probabilistically checkable proofs, and we'll come back to our question about what are the high dimensional properties that we need of the complete complex. So what is a probabilistically checkable proof? A probabilistically checkable proof is just an alternate characterization of NP. Classical notion of NP says that what are the languages in NP? It's exactly those languages in NP which are polytime checkable. That there exists a polynomial time verifier such that for every string x, there exists a proof y such that the verifier will accept the pair xy if the string is in the language, and if the string is not in the language, no matter which string y you provide to the verifier will always reach. This is the classical notion of NP. It's exactly those strings for which there are short proofs of membership. But PCPs state that there's an alternate way in which this proof can be rewritten. So then the classical notion of NP, the proof is checked by a deterministic verifier which reads the entire proof, its entirety. For example, this could be a 3-sat formula, and you're checking if it's satisfiable or not. The corresponding proof is one such candidate proof is the assignment, and the NP, the verifier basically has to read the assignment to check if it is proof of. What PCP state is every such proof thing can be rewritten. Every such proof can be rewritten in a slightly possible longer format, which is now checkable not necessarily by deterministic verifier, but by a randomized verifier, but which checks the proof very locally in the sense that it tosses log n points. It becomes more powerful by tossing log n points, but then it queries the proof in at most some constant number of locations, so k order 1 location. So it's basically it's not going to read the proof in its entirety, it's going to read the proof in very few locations and yet be convinced that the proof is correct. For instance, More specifically, if the string is in the language, then there must be one such proof that convinces the verifier that the string is in the language always, all the time. And most importantly, when the string is not in the language, when X is not in the language, then no matter which proof pi you provide to the verifier, at least two-thirds of the time, even though it looks at only k locations in the proof, it's able to detect an inconsistency and it rejects the proof. So this is what it says, that you can change every language that is checkable in the classical notion of NP as also this way of checkable, in which the verifier looks at the proof only at very, very few locations. It only looks at k locations. This is not going to dwell too much into these things, but it says that every proof has this corresponding of any proof that is checkable in the usual sense has this PCP way of writing it, in which you just look at the proof at k locations and yet are convinced with very high probability that the proof is correct or wrong. Now, where do hypergraphs and all come into play given this? So given any PCP, there's a very natural hypergraph that you can construct out of it. It's what I'll call the Pcp hypergraph. It's this following object. The vertices of this hypergraph are the proof locations, and the hyperedges are going to be the set of k queries that participate in this proof. So it's a very, once you're given such a PCP, you can exactly, so for every random point, you have a particular set of k locations you're looking at. These are going to be the hyperedge, and you can build this hypergraph out of a PCP. The PCP exactly contains the vertices are all the proof locations, and the edges, the hyperedges in this are exactly your set of k queries in this object. And while studying PCPs was a very interesting object for us who think to trying to construct PCPs, is what we would like to answer is, which are these hypergraphs that supports PCPs? Under which hypergraphs can you actually construct PCPs? Which one? Of course, a natural answer is certainly the complete complex. If at all there exists any hypergraph, then this one supports, because it supports every possible k query. And what we are actually going to be interested in is, are there sparser hypergraphs which also support PCP? And this is what we'll try to study later. We're going to ask, are there sparse hypergraphs? And the reason for studying is, while studying PCPs, it happens to be an important, the number of hyperedges happens to be a very important measure. So we want to come up with a PCP for NP in which the number of hyperedges is as small, as few as possible. And that's why we'll be interested in the sparser notion of hypergraphs. So the question we're going to ask is, what are the hypergraphs that supports PCPs for NP, for say some problem in NP, say 3-SAT or 3-coloring or something? We want to construct which are the sort of hypergraphs which are going to support these PCPs. And so how does one answer this question? So let's look at some of the basic building blocks.
Prahladh?
Yes?
There's a question.
So you want it to be stopped, right?
Yeah?
That's a good place. So your goal is to make the set of k queries a small set, yes?
Sorry, I can't shaft. Is it shafted?
Your goal
Yeah.
is to make you said that your goal in going and thinking about expanders is to answer questions about PCPs. And the question that the goal that you said about PCPs was to make the set of k queries a small set, yes?
Yeah, so one of the goals, one of the important parameters, I want to keep this PCP, it's sort of related to the randomness of the PCP. I want to keep this will be related to the number of hyperedges that participate in this graph, and I want to come up with a PCP which has as few hyperedges as possible.
No, I get it.
So that's,
I just think it's probably useful to explain why. So in other words, having a small set of k queries, what does that correspond to in terms of the resources of the PCP? So you want to make a more efficient PCP, yes?
I want to make a more efficient. So in some sense, it will. So if you look at these two pictures I had before, so there was this length y, which was the original NP proof, and then I was said that the NP proof can be rewritten in a slightly longer format, which has this much more efficient way of checking it. And how much longer will exactly correspond to the will roughly correspond to the number of hyperedges. And this is a very useful notion when studying PCPs with respect to, PCPs are used for in approximability and stuff, and this is an important notion to keep. And so that's the reason why we are,
so to summarize,
one focus of interest to study are there sparse hypergraphs that support PCPs for NP.
So can I ask the same question again? I had the same question. Why,
It's
so
the size
he
of the
can't
group.
see me, I think. I'm to the left of the barrier, but
Size of the group.
but it's
You
not the
also make
size,
a-
it's the number of edges. The size of the proof is the number of vertices. This is the number of edges, so I don't see the connection.
So the proof, yeah, it is true the size of the proof seems to be the number of vertices, but typically when you do these objects, what you actually care, the proof, when you study inapproximately, what you actually care is not the size of the number of edges, but the number of randomness of the verifier, and that actually happens compared to the number of hyper edges. The actual quantity there is not the length of the proof, but the number of random coins tossed by it, and that happens to be the number of hyper edges while studying PCPs.
The number of random coins tossed by the verifier when he makes queries?
Not the number of the exponential in the number of random coins will be exactly the number of hyper edges in the graph.
And maybe an alternate way to say it is that if you think of it as a CSP, it will have few constraints or something. So if you
If you think of it as a CSP, it's one with the least you want a CSP with as few constraints as possible, yes.
But it's also true that this is a bit simplistic in the sense that if it's a component in a PCP construction, then maybe at a later stage you make every hyperedge become a proof location. Actually, that's what happens, for example, when you do parallel repetition. And then actually having few hyperedges does correspond to having a short proof.
Yeah, so in some sense, when parallel repetition, or even when you do the first, you need to compose this proof, immediately the number of random points, the number of hyper edges becomes the proof length rather than the actual proof length of. Yeah, so if
I would summarize that
This-
it's related, but it's not exactly.
it's not the same. It's not the same. All I want to say, it's an important parameter to keep in mind for various other reasons while studying PCPs, and so I want to construct the hypergraphs or these KCSPs, as Venkat was stating, in which the number of constraints is as few as possible.
maybe a related way to say what Edith is saying is if you make it a label cover, then now the number of variables will be equal to the number of constraints.
Yes. Yeah. Okay. So I want to see what are these sort of hypergraphs that support PCPs for NP. The way we'll sort of do it is we'll look at the existing constructions for PCPs and see some of the basic building blocks and see what are the hypergraphs that naturally arise while doing this construction. So some of the building blocks that go into PCPs, one of them was already mentioned, parallel repetition. This is one of the building blocks I mentioned. Some other building blocks are the low degree test. Then there's linearity testing due to Blum, Loewe, Rubenfeld. There are a few more others like the long code testing, which is actually just a souped up version of the linearity testing. And then there is also gap amplification. In fact, these are just the basic 5 building blocks. Almost every PCP that I know of is just a combination of some of these building blocks. For the purpose of this talk, I'll just focus on 2 of these, the low degree test, linearity testing, and see what are the hypergraph structures that come out in these while one studies these objects. So let's begin with possibly the simplest of the lot, the linearity testing. So here we are given some function f on the Boolean hypercube. We are given a Boolean function on the hypercube, and we want to check if this function is linear or far from linear. What I mean by linear is f of x plus y is equal to f of x plus f of y for all x, y. And Blum, Loewe, and Rubenfeld suggested the following very natural test to do it. They said just pick 2 points x and y at random from the Boolean hypercube, query f at the 3 points corresponding to x, y, x plus y, and accept if this predicate is satisfied. F of x plus y is f of x plus f of y. And they showed that if the function is in fact linear, this test will pass with probability 1. If the function is far from linear, this test will reject with considerable probability. So this test sort of detects linearity or far from linearity. It's very robust to how far the function is to linearity. That's, of course, that's the completeness and soundness of the test. What I'm more interested in is what is the corresponding hypergraph structure that you get from this. Here, so you're viewing the input as this, you're viewing the function, that is a function as an evaluation of you're viewing the function as, you're viewing the input space as points in a Boolean hypercube, and you're looking at various sets of triples of points, not arbitrary triple of points, but triples of points corresponding to x, y, x plus y. So you're considering only these. So the hypergraph structure of this particular test refers to is you view the input space as the Boolean hypercube, and you can look at these sort of triples, x, y, x plus y. These are the hyperedges in this case. You have hyperedges of uniformity 3, and you're looking at these hyperedges. These are the particular hyperedges that arise when you talk about linearity test. Let's keep this in mind. Let's move on to the next. So this is a particular type of hypergraph structure that comes when one builds PCPs using the linearity test. It's these, we view the input space as 0, 1 to the n, and the hypergraph, the hyperedges that arise are these triples of points, x, y, x plus y. It's not 3 random points, it's 3 correlated points, x, the first 2 being random and the third one being the sum of the 2. A test of a very similar flavor is what's called low degree testing, in which here you're no longer working with the Boolean alphabet but over a large field. You're given some function which is you're given the truth table, you're given the evaluation of some function on an m-dimensional space. And what you want to check is this function, f is some finite field over here, a large finite field, and what you want to check is f low degree or is it far from being low degree? And once again, as in the Booleanity, there's a very natural test for this. So this is the picture shows a sort of the m-dimensional space in which you're trying to check, and you're given the function specifies a value for every point on the space, and what you want to check is this function the evaluation of a low degree function, or is it far from being a low degree function? Let's not go into what a low degree function and stuff are, but there's a following very natural test is just pick a random affine line in the space, query f on all the points on the line, and check if the restriction of this function to this line is a low degree polynomial. And once, as in the linearity test, what is known is if the functions are actually low degree, then this test will pass with probability 1. If the function is far from low degree, then in fact this test will detect the fact that the function is far from low degree, though it looks at the function at a very small number of locations. It just looks at the function on one line. The linearity testing looked at the function only at 3 points, and yet it's tell. So what I want to specify over here is, once again, let's look at what's the corresponding hypergraph structure that we have with the low degree testing. We are viewing the input space now as an m-dimensional vector space, and the hypergraph structure are corresponding to lines in this one. You're picking up Q. So if Q is the size of the field, you're having hypergraph of hyperedges of size Q, which corresponds to points on the line. You're only looking at these sort of hyperedges in this graph. The hyperedges corresponds, each hyperedge that's defined by this test corresponds to the lines in this particular low degree test. And these tests, both the linearity testing and low degree testing, come very handy in constructing PCPs. In fact, most ways of this is not spelled out explicitly, just like the Johnson graph came about naturally while trying to study the complete K-uniform hypergraph. What are called the corresponding notion over here is the Grassmann graph will come comes naturally when studying either the low degree analyzing the low degree test or the linearity testing. And what are these Grassmann graphs? The Grassmann graphs are these following things. It's almost analogous to the Johnson graph. It's the graph whose vertices are the set of all d-dimensional spaces in FM. I'm sort of going to be sloppy over here, whether it's linear spaces or affine spaces. You could work with one of the two. So when Grassmann usually refers to linear spaces, though in my examples these have been affine spaces. The vertices are these, and the edges of this object are pairs of, you connect two d-dimensional subspaces if their intersection is of dimension t. So this is what the Grassmann graph is, and the Grassmann graph very naturally comes when one tries to analyze. It's not explicitly spelled out in the early results on low degree testing and all, but later results actually do have the Grassmann graph appears explicitly in the proofs trying to prove low degree testing. If you look at this object, a bit closely, you look at it, the Grassmann graph is actually in some sense a sparsification of a related Johnson graph. So the Grassmann graph over the field F with parameters m dt is actually a sparsification of the Johnson graph with parameters q to the m, q to the d, and q to the t. This is not hard to see. This graph is just a subgraph of this corresponding Johnson graph, where q is the size of the field. And in that sense, the Grassmann is already a sparsification of, in that sense, what I'm trying to say over here is the PCPs that are constructed out of low degree tests and linearity tests, the hyper edges typically are going to correspond to like Grassmann graphs, this ones, and they are in some sense a sparsification of the corresponding complete K-uniform hypergraph in this sense. You can ignore that this one. And just another thing about the Grassmann graph, just like the complete K-uniform hypergraph had a very natural simplicial complex associated with it, there is another complex associated with the Grassmann graph, which is the subspace complex, in which, just like we layered up the various subsets of a particular size, here you can layer up various subspaces of a particular dimension, and you look at the natural containment graph. This is what we call the subspace complex, and a Grassmann graph will naturally have the subspace complex. Now, what we talked about right now is, I want to understand, once again, we want to understand what are the hypergraph structures that come about while trying to study PCPs. We saw that two of the building blocks are low degree tests and linearity testing, and they have these Grassmann graph-like structures. Those are the hypergraphs that come about while trying to study them. Seem to be fairly involved, so we'll go to an even more simpler building unit and try to understand what's the underlying hypergraph that you come about when you're trying to study this. So this is what we'll go to, and then we'll try to understand what's the corresponding hypergraphs. We talked about low degree testing, linearity testing. An even simpler unit than both of them is what's called agreement testing. And this agreement testing actually appears in both of them. It tries to abstract out the following feature of all the previous two tests. In this, you specified some global object, f, say on n points, but you're not specified, the global object is not specified in one global fashion, but it's specified as an ensemble of local objects. You specified the global object, just for say, for instance, you specified it for every k-size set. You're told what the function is on every local view. You're not specified the function globally, you're only specified it locally. You're specified the function for every k-size set. And what you want to ask, suppose I gave you this specification instead of the global specification. I gave you the specification as an ensemble of local functions instead as a single global function. You can ask, do the ensemble of local functions, can they be actually suit together to form a global function? Can they actually be patched up together? That is, of course, if one obtains the ensemble of local function honestly from the global function, then they can be. But there's no reason why the ensemble of local functions are obtained. So basically, for every k set, the ensemble of local set says for every k set, I'm going to give a function on that particular k set, and I'm going to give you this ensemble. This is the way I'm going to encode a global function. I'm going to ask, do these local functions actually arise from a single global function? This is the question we're going to ask. This is sort of a common feature that happens in both the linearity testing and the low degree testing. Linearity testing, for every triple of points, you're given values such that they satisfy f of x plus f of y plus f of x plus y is 0. And you ask if all of these can be glued together to get one global function. In the case of low degree test, you're given for every line, you're given a local function, and you ask if these things can be glued together to get a global function. And here we're asking a much more general thing. You're asking for every k set, I'm giving you the local view of the function, and I'm asking, can these local views be glued together to get a global view? So let's try to make this question a little more formal. So once again, we want to ask, when can the local ensemble of functions be sewed together or glued together to form a global function? The way I stated it, you need perfect, if you want to get a single global function that explains the whole thing, you need perfect local agreement. All the local views should perfectly match with each other. That is, whenever two local views are talking about the same object, they should completely match, perfectly match. One way of stating this is, take any t smaller than k, the k is the size of the k set we're looking at, and take any subset of size t, and take two subsets s and s prime that extend this t, that is t, s and s prime, and if we have that the two local functions completely agree on this intersection t, this is what we call perfect local agreement. That's what we call perfect local agreement. You need perfect, if you want to have perfect global agreement, that is, if you want one single global function that fully explains the local functions, one would need to have perfect local agreement, and this is not hard to see at all. One can easily show If you have perfect local agreement, the way I have written it out there, then one would have perfect global agreement. This is not too hard. In fact, one notice that the only thing that this proof will require is that the Johnson graph corresponding to JNKT is a connected graph. It's not hard to see this. So once you see that the Johnson graph is connected graph, you will realize that perfect local agreement will imply perfect global agreement. But this is not the sort of theorem I'm looking for. I'm asking, what about if we don't have perfect local agreement? Suppose we have only approximate local agreement. Agreement locally happened most of the time, possibly not all the time. Can we still say something non-trivial about the function? Can we still say some form of global agreement? So now let's try to see what I mean by this definition. So what I mean now is I want to talk about approximate local agreement. What I mean by approximate local agreement is the following thing. So once again, we are given this. So what's the input? The input, as I had mentioned before, is this local ensemble of functions. We have this local ensemble of functions, and we want to check if they can be glued together to form, such that they arise from a single global function. You have a local ensemble for every k-set. I've specified the value of the function on the k-set. I'm asking, is there a global function that explains this data? And let's look at the following sort of local versus global agreement. So local agreement here I'm going to talk about is the one way to test whether the functions are locally consistent with each other is pick a random p set of size t and take two random extensions of it, two k sets of size, two sets s and s prime of size k, and check if the corresponding local functions fs and fs prime agree on T, on the common part. They agree, and let's ask how frequently does this happen. Suppose this happens not perfectly all the time as before, but most of the time. It happens, say, with 99.99%. Then can we say that there exists a single global function that explains most of the data, that there exists a single f such that for most k sets S, the restriction of f is in fact exactly the local function, agrees with the local function, let's say with 0.98% probability. What we want to ask, what you ask is, does local agreement imply global agreement? So is this question sort of clear here? So we have this object, we don't want to specify this local object, this global object. You're not specifying it in its raw format, but you're specifying it as this encoding in which what we're giving is just a local view of the function for every k set. We're just giving the k set. And we want to ask if you give these k sets, if I give you some function like this, when can I guarantee that all these local views can be glued together to get a single global function?
Prahladh, can you dwell on why you're assuming linear dependence, why O of epsilon and not some function of epsilon?
So this doesn't have to be. All I want is some 1 minus epsilon and some 1 minus delta over here.
Okay.
The reason I stated is the current results have this flavor.
Thanks.
Yeah, so right now I just want to say, can we say something non-trivial? If I have a non-trivial local agreement, can I say, if I have a moral local agreement, can I say something? This need not be order epsilon, it could be some other delta. Yeah. And strange thing is when you are working with a complete complex, the answer to this is S. And this is a non-trivial theorem which was proved by a sequence of works the most recent of which being Dinur Goldberg, Impact as a Cabinet Wigderson, Dinur Steurer, Dinur Amon, and Irit, myself, and Yuval, in which we show some theorem of this form, that is for certain setting of parameters, if k is not too large compared to m, and t is bounded both from above and below, then local agreement does imply global agreement exactly the way I stated above, in which you have the 1 minus order epsilon. The different setting of parameters will change the order epsilon to something else. So we do have such a local agreement implies global agreement, and in fact, it's not just that, we can show that the majority decoded function is a candidate global function S. So you do have, and this sort of local to global sort of phenomenon happens in all these tests, with the linearity testing, loadability testing. You get to see the global object only locally, and some local consistency is satisfied, you're able to build this global object, and you're able to show that if local consistency is satisfied, then it must be because there is a global object that explains the data. And what these theorems tell you is the complete K-uniform hypergraph does support such a local to global agreement testing result. That's the statement of these results. And what we would like to ask is, are there sparser versions of the complete complex that also satisfy this local to global testing theorem? Yeah.
Prahladh, why is an upper bound on T natural in your theorem there? I mean, is it because so in your theorem which you just flashed, yeah, there's an upper bound on T also. Isn't larger T sort of somehow giving you more information in the local agreement, or?
Yeah, imagine T equals K.
So there are counterexamples when T goes all the way to K minus 1 and all you can give. You can't. So we don't have the strong. We don't yet have the best form of theorems for these. So when T goes very large, we do have. You won't get this 1 minus order epsilon sort of results. And in fact, you can come up with, because if you notice the Johnson graph, what's going to happen in the Johnson graph, the movement is very little. If the random walk, because you're moving from one K set to another K set, only if the agreement is K minus 1. The diameter of this Johnson graph is very small, is very large. Therefore, you can ensure the fact that you can come up with counterexamples which, when T is very close to K.
Okay, so it's not just a, artifact of the theorem or the current proofs, but it's something fundamental.
Something fundamental. We do believe that we can say strong. We have counterexamples to the theorem as it is stated. We do believe that these counterexamples are the worst possible counterexamples, and one would like to prove this. We don't have theorems to that extent, that effect yet. So we have only a good understanding when T is bounded from K on both ends. When T is very close to K, we don't yet understand this. What happens to local versus global agreement? Because we have counterexample to the current theorem statements. They could be other statements which explain that those are the only counterexamples that happen. For example, a very natural let me actually take this offline, depending on how much time. I can give you counterexamples when T is like K minus 1 or K minus a constant.
Okay, maybe just add that actually this is where you can see the expansion happening, because when T grows very large, your random walk is kind of not expanding very fast. Yuval said, if T equals K, you never move, you stay in place, right? So you certainly don't expect this to work. And if T is K minus 1, you're moving slowly, so somehow someone can cheat you by putting a different function in the vicinity of a specific K set, and you won't notice it until you made enough steps.
Yeah, so in some sense, basically you'll be looking at the Johnson graph J and KT, and when T is very close to K, there are small sets that don't expand. And you can use those small sets to come up with counterexamples. What we would like this theorem is to show that those are the only counterexamples to this theorem. We don't yet have such a statement, but there are counterexamples, because when T is very close to K, the corresponding Johnson graph is a non-expanding graph. Johnson graph is a non-expanding.
So
it's not expand in the usual sense.
How fast do you want the random walk to mix? Like log K-ish?
I mean, if you want this O of epsilon, the one step should have second eigenvalue constant. If you're moving slower, then you expect that to exactly appear in that O of epsilon.
Okay. Any other questions? I can't see that side of the audience at all. Let's continue. So what I've shown, what we said so far is this complete K-uniform hypergraph has this very nice local to global feature. You can check, that is, you specify a function only very locally. You specify it by giving it on every hyperedge, but yet if some form of local consistency is satisfied, you can say that these local paths can actually be glued together for the most part to a single global function. Now what I would like to ask is, are there even partial versions? Do you need to actually use the complete K complex, the complete K-uniform hypergraph to do this, or are there sparser versions of the complete complex that also have such a local to global agreement testing theorem? And what was recently shown is actually, yes, there are these sparse versions of the complete complex which are far fewer edges. In fact, the complete complex has n choose k, something like n to the power k hyperedges, there are these Ramanujan complexes which are only linear in n edges, and they also have the same property as this exact same theorem can be proven by this. This was a result of Dinur-Kaufman from a few years ago. They showed that this specific complex, this is a different complex, it's not the complete complex, it's a much sparser version of the global, and it also has the same local to global feature to it. And actually, what I want to mention at this point is, so in some sense, the Ramanujan complex here is sort of mimicking the complete complex for the purpose of this agreement testing. And we would like to understand in what sense it's mimicking. What is the property of the complete complex that the Ramanujan complex also has that is sufficient for proving this local to global agreement theorem. And I want to mention that these are not the only places where we have seen such sparsification. There have been a few other instances while studying PCPs in which we know such sparsification. We have an existing test, and then we show that there's an even sparser test that actually is sufficient for the purpose. And actually these two sparsifications have come about in the context of linearity testing and low degree testing. So let me briefly mention what are these sparsifications. The linearity testing, as I mentioned, is you're given a function, you're given a Boolean function on the Boolean hypercube, and you want to check if it's linear or far from linear. And Spielke and Wigderson had obtained a sparsification using epsilon bias sets. Basically, they said take the same DLR test, but then instead of choosing the second point to be a completely random point, choose the first point as before. Choose the first point x to be a completely random point, but the second point, choose it only from an epsilon biased set. And still, you can more or less show up to some error epsilon, the test will go through. Exactly, you'll recover the same property. So this is a much sparser version of the BLR test. The number of hyperedges have reduced considerably. You're choosing x randomly, only one point fully at random, and the next point from a significantly smaller size set. And what Spielke-Wigderson showed is this test is enough to capture, basically to prove the BLR test. Even such a sparse hypergraph is sufficient for the BLR test. In the context of low degree testing, a similar result was proven by Bensasan, Sudan, Vadan and Wigderson using epsilon bias sets and subfields using Moshkovitz and Raz, where you have the same theorem as before. You remember the low degree testing in which you pick an arbitrary line and check the restriction of the function to the line to check if it is low degree. What these works show that how do you choose an arbitrary line? A line is chosen arbitrarily. A random line is chosen by first choosing a random point and then a random direction. This is how one chooses a random line. They said you can choose the line by using much fewer bits of randomness. Just choose a random point and choose the random line, not from a completely random direction, but only from an epsilon bias set, or from a direction specified by a subfield, not by the entire field. And they showed that even if you restrict yourself to this class of lines, which is a much smaller set of lines, you can prove this same low degree test. The low degree test has the same feature as one. So what I'm trying to say is, we know all of these sparsifications. The linearity testing, there's this sparsification using epsilon bias sets. For the low degree testing, there's a sparsification using epsilon bias sets or subfields. For agreement testing, there's a sparsification using Ramanujan complexes. And what I want to understand is in what sense do these sparsifications mimic the original object. In the first two cases, it's a subspace complex. In the last case, it's the complete complex. There is some sense in which you could replace, for example, in the agreement testing, the complete complex by this much sparser object, Ramanujan complex, and yet prove the same theorem. So what is the property of the complex that's needed in each of these things? And if you look at these closely, one natural, look at these proofs, if you go into the proofs of all of them, happens to be there's a natural random walk associated with all these complexes, and you want some property of this random walk that is sort of mimicked by these smaller sparsifications. So what I will do next is actually tell you what this random walk is there, of what's the random walk, and once I define the random walk, it will be clear why at least the first two sparsifications have this property. So now let's go back to our notion of a complex. So a complex is once again this layered object, and we're going to define a random walk on a specific layer, on a layer xi. So we have this complex, it's a k-layered complex. We're going to talk about a particular random walk on just the layer I. So you're going to move from one vertex in layer I to another vertex in layer I. We're going to talk about two random walks. One is what I'll call the up-down random walk, and the other is going to be the down-up random walk. What's the up-down random walk? The up-down random walk is, I'll tell you how to move from a particular vertex S to another vertex S prime in this layer I. So, one way to do it is, the up-down random walk is you go to a set, go to an R in the layer above, go to R in the layer above, but from the appropriate distribution, from the distribution pi I plus 1, condition on the fact that the set above contains the smaller set, and then choose a random subset of that set above and pick S prime. So the up-down one, you move one step up according to maintaining the distribution and move one step down, and that's going to be the up-down walk. That's the walk defined on the layer below, the up-down walk. And the down-up walk is a very similar walk in which you do exactly the reverse process. That is, you sort of go to, given a set S, you pick a vertex, you pick a set of one level size lower from a lower layer from the appropriate distribution, and then pick another set that contains this T from the layer above, in the same layer Xi. So these are the two distributions. This is the up-down walk and the down-up walk, this one. The way I stated it, these two walks seem to be very, very similar walks. They look very similar, but let's actually look at it even for the complete complex. These are actually two very different walks. So suppose you moved from a set S. Suppose I was the set of vertices, the set of k sets. This was a set of k sets. S was chosen for the set of. You're picking a random set of size I plus 1. So you're moving from a set of size I plus 1 to another set of I plus 1 in both the up-down walk and the down-up walk. Notice that both these walks have a lazy component. That is, there is a considerable probability. There's a probability that you'll come back to the same vertex that you started off with. That is, you start with vertex S, you could come back to S prime, and notice that these two walk, the lazy component of the up-down walk and the down-up walk are very different, even for the complete K-uniform hypergraph. These are going to be very different for the lazy component of it. Of course, once you shave off the lazy component, these two walks happen to be exactly the same walk for the complete K-uniform hypergraph. But these two walks, what I want to just say is these two walks are two different walks. They have different lazy components. The probability that you come back to the same starting point is different in the up-down walk and the down-up walk. So let's have this nature of walk, and let's look at this up-down walk and down-up walk for the case of graphs which we are very familiar with. So we just have this regular graph. We have this three-layered graph. The first layer containing the empty set, the vertices, and the edges. Let's try to understand what the up-down walk and the down-up walk is. Now, recall when we talked about the graph, we talked about two sort of random walks on it. One is just choosing a random vertex, a completely random vertex. Notice that this is exactly the down-up walk, because you just go to the empty set and go to any other. So consider this is exactly the down-up walk on the set of vertices. The down-up walk on the set of vertices is exactly choosing a random vertex in the graph. And what's the up-down walk? The up-down walk happens to be the other walk which we associated with the set of vertices is to, from a vertex, pick a random neighbor and go along, go to a random neighbor. This is exactly the non-lazy component of the up-down walk. So if you recall, our definition of expander was exactly this object. We said that these two walks, picking the first walk which is choose a random vertex and the second walk which is choosing a random walk on the graph, picking a random neighbor, these two walks were closed in spectral norm, and this, when rewritten in terms of these walks, this is basically stating that M0 down minus the non-lazy part of M0 up is small in spectral norm. This is exactly the usual notion of expander graphs. And what I want to claim is, let's just extend this definition to the higher layered component, to the high dimensional components. We say that suppose you're given this k plus 1 layered object. I'll call it a lambda h dx if it has the following property. For every layer I, the down-up walk minus the non-lazy part of the up-down walk, the spectral norm of this difference is bounded by lambda. It's not just for the 0 level, but for every single level you have this sort of thing. So this sort of a natural generalization of what we had for expanders. Expanders just talked about this random walk on the set of vertices. Now I'm talking about a walk on every single layer of the simplicial complex. So for each of these layers, I want the down-up walk to be close to the non-lazy part of the up-down walk. And if you look at this definition, it's not too hard to see that, firstly, the way we defined it, it's exactly generalizes the spectral definition of expanders. And it's very easy to see that the complete complex and the subspace complex, the complete complex and the subspace complex do satisfy this property. They always have the property that they are bounded and this norm is small. And if you actually go back to these objects that I have talked about, these sparsifications I talked about, each of these sparsifications actually work because they have the same HDX property in them. In the proofs, if one goes into the proofs, each of them and looked at them carefully, the reason these sparsifications work is because this corresponding graph, the corresponding layer to the complex over there had this HDX property. So this is the property which I'm going to sort of, at least for the purpose of this talk, call a high dimensional expander. That is, if we're going to view this K uniform hypergraph as the simplicial complex, we're going to define this notion of a walk and two walks on each layer and sort of say the up-down walk and the down-up walk should be sort of similar to each other in this sense. If this is the case, we will then call the corresponding complex a lambda HDX. We will see other definitions of lambda HDX. We will see in Irit's talk yet another definition of what it means to be a high dimensional expander, and we'll actually see later on that that's equivalent to this definition. And it is this definition which sort of happens to be at the heart of all the three sparsifications that I had mentioned. It's because those corresponding complexes had this sort of HDX property, we were able to prove those results for the much sparser versions of those objects. Yeah, so this is going to be finally what's called, this is what we will call as a random walk high dimensional expander. The random walk high dimensional expander is an object which has the feature that the up-down walk and the down-up walk on every layer are close to each other if you shave off the lazy component of the up-down walk. Any questions on so far? So this is what we finally come to, that is, yeah.
Hi, so for the complete complex, I guess you could even take lambda as small as you want in this definition. Like basically, you said that the...
Sorry, I can't hear you.
Sorry, so for the complete complex, one can basically take lambda as small as one wants because these two operators we said are the same, right?
Yes.
Yes, for the subspace complex, is it still the case that the two blocks are identical, or do you need, is it like some value of some constant lambda?
If you shave off the non-lazy part, in both in the down-up and the up-down walk, they become identical in the subspace complex.
As well, okay.
Just like in the complete complex. If you shave off the non-lazy parts, they become identical.
But the down walk also has a lazy component.
Pardon?
The down walk also has a small lazy component, so it won't be exactly the same.
We are neglecting in this definition because that seems to match with the graph definition. We do have, we retain the lazy component in the down-up. The usual definition, even for graphs, we always have retained this one. So we're going to retain the lazy component in the down-up walk, but we will not retain it in the up-down walk, we'll shave it. And the reason being, when k is much smaller than n, the lazy component in the down-up walk is very, very small, it's insignificant. Compared to the lazy component in the up-down walk, that's a significant component, and so we shave that off. So it seems strange that you're not shaving it off on both, but this is what we were doing even for graphs. We did not shave off the lazy component of the down-up walk. We always retained it. So in that sense, if you want to generalize it, we have to retain it for the down-up walk in graphs. We retain the lazy component, but only for the up-down part we remove the lazy component. Any other question? Was that a question or? Okay. So in this sense, it's sort of, this is an object, and if you go back to these proofs, these proofs were not written this way, but if you go back to these proofs, for all these three proofs, the sparsification for the linearity testing, sparsifity for the low degree testing, and the agreement testing, you notice that the reason those proofs work is because the corresponding sparsified hypergraphs or complexes have this high dimensional property. The reason they work is because in each of these cases, the corresponding these random walks, the up-down random walks and the down-up random walks, behave very close to each other. By the way, I think it should be good to actually get an example. I want to say that the up-down walks and the down-up walks can actually behave very differently from each other. I can give you examples. Let me try to see this. I don't know if you see this. Let me change. Do you see this?
Yeah.
Yeah. So let's consider the following graph. Let's consider the following. I'm going to consider following three uniform hypergraph. Can you see what I'm writing?
Yes. Yes.
In which the vertex set is this following 1, 2, 3 cross 0, 1, 0, 1. And the hyper edges in this graph are this triple of such that in all the first components are all different, are three distinct things, and the second components sum up to 1. Let's look at this hyper edge. It consists of, these are the triangles in the particular graph. So if you look at this hypergraph, x minus 1 of course is the empty set. x0 is all the vertices. If you look at what are the edges in this graph, which is the only component which I haven't written, x2 of course is exactly h, and x1 is set of all ax, by, such that a not equal to b. There is no condition on the x's, on the xy's. This will exactly be the edges in this graph. Let's look at what the up-down walk and the down-up walk is. Notice the up-down walk. Look at what are the triangles. The triangles correspond to and connecting 1x, 2y, and 3z. Form a triangle if x plus y plus z equals 1. This forms a triangle in it. Notice the up-down walk on the edges will only move from an edge to another edge in the same triangle. It will never go out of the triangle. The up-down walk always stays within a triangle. It never can move out of the triangle. Whereas the down-up walk, it can move from one edge to another edge, and it will eventually reach all the edges. The down-up walk is actually a connected graph on this. So I want to claim the down-up walk on edges is very, very different from the up-down walk on the edges. The up-down walk is not even connected, whereas the down-up walk at least is connected. So this is an example of a graph in which it's a hypergraph for which it's not, forget about being a high-dimensional expander, these two walks are just not connected with each other.
Prahladh, just to make sure, addition here is in integers or mod 2?
I'm viewing them as elements from GF2.
Okay.
So all you want is that you have a Steiner triple system, right? I mean, this is a particular case, that every edge is contained in a unique triangle,
Right.
so that you can't...
So every edge is contained in a unique triangle, therefore the up-down walk will only move within the triangle.
Right.
It will never leave the triangle, whereas the down-up walk can move from an edge in a particular triangle, it can move to edges of other triangles also. So this is an example of actually this is not surprising that this is an example which comes while studying with parallel repetition. So there are cases of graphs, this is not a, okay, that's so much for this example. Let me go back to my slides. You see my slides again?
No?
What do you see is, sorry.
Yeah.
How am I doing with respect to time? About 5 minutes more or?
Yeah.
Yeah. Okay, so we define this notion of high-dimensional expanders. Okay, so all that's nice. We've seen saw that there were a few constructions that came about in PCPs which do satisfy this. We can ask is now, given that we have this definition, can we construct such high-dimensional expanders? So we talked about the sort of sparsification of, we said we wanted a K-uniform hypergraph which has this property, that is, in every layer, the up-down walk and the down-up walk, after removing some lazy components, look similar. And the natural first thing to do is to pick up this graph using, pick a random hypergraph and check if it is a high-dimensional expander. What one can notice is if you pick a random subset of size, so if you want to pick a K-uniform hypergraph and if you pick a random set of hyperedges of the number of hyperedges being n to the k-1, it's easy to show that this is actually a lambda HDX, this object, and this is proof of this generalizes the random construction of expanders. Show the random graph as an expander, it's exactly the same proof. And strangely enough, it also shows that there's too much structure expected of this definition. That is, if you take slightly sparser things, like say instead of n to the k-1, n to the k-2 or not, you can show with high probability these are actually not HDXs. In fact, if I don't know how to show a random object, there even exists such a HDX in this way. On the other hand, we do have these explicit constructions of some of these HDXs due to Lubotsky, Samuels, Vishnay, and Kaufman and Oppenheim. So it will be interesting to find out if there are other constructions of such high-dimensional expanders. So unlike the usual notion of expanders in graphs, a random object does not seem to satisfy this property. So till the explicit constructions, we did not even know if such objects, if they were sparse such objects. It will be good to find out if there are other random models under which we can show such sparse constructions, and we don't know this. It will be good to find out other possible ways of doing. The only known constructions of sparse HDXs are from these two constructions that we mentioned below out here. More or less, I'm going to summarize. So we eventually saw what are high-dimensional expanders. There are a few this ones, and I think these objects are useful for PCPs. As far as we try to hand them, we might be able to construct even PCPs with better parameters. I don't yet know how to do this. This was motivating goal for trying to come up with better PCPs is trying to study these objects, and I hope the next 1 month will lead to some such interesting applications. I'll stop with this.
Okay, thank you very much.
Any more questions about the talk before we?
So if you want to, you just, okay, I'll try to shout so since I cannot see. You just talked about the up-down and down-up one level, but your test had like K and T which are far apart. So if you jump from K to T and go back up, that is somehow composition of these down-up and up-downs in some natural way?
Yeah. So we will see this. These up-down walks are themselves, an up-down walk itself can be decomposed as one up step followed by a down step. And we will see this later on actually in the spectral thing. We will actually look at, you will break it down into K minus T down steps and K minus T up steps again. Yeah, so we will do, in fact, in the spectral treatment, we will be looking at these we'll be looking at these, we'll be not looking at these up, down and down, up. We'll just be looking at one step up and one step down and looking at those particular operators and looking at them from a spectral viewpoint.
Thanks.
Which will help you to answer all the questions you asked here.
More questions?
So I don't see the connection between these agreement tests and PCPs. Like, basically, what is the goal? Like, okay, so I mean, we can now do agreement tests. What is next? Like, are there questions here?
Sorry, I couldn't fully follow what's the relation between agreement tests and PCPs or agreement tests and...
Right, we can do agreement tests now, but okay, what is the next question? Are there other tests we're looking to do, or are there actual PCP questions we're trying to answer?
Okay, so we can do it. So okay, so the point is, agreement test is it's sort of the basic building block in this sort of thing. You should, at the very least, have an agreement test. Now, the agreement test, the building block should be powerful enough to encode an NP computation. So, when you work with low degree testing or so, the low degree polynomials were powerful enough to sort of encode computations and stuff. So, we don't yet know the sort of objects you get from the Ramanujan complexes and all have the feature to do it. If they had, then you could build a whole PCP over them. We don't yet know, I don't yet know if we can want to do that. That might be the next goal, one of the goals.
So you don't know anything for low degree polynomials, any sparse test in this sense.
Right, so a great question would be, just like these Ramanujan complexes sparsify the Johnson graph, what would sparsify the Grassmann graph? And you would like to have a constant degree specification. This is an open question.
And do we expect that this works? Is it are they counterexample or is it a matter of proof?
Look, I used to be certain that you cannot sparsify the Johnson graph to a constant degree, and I also tried to work on it, but I luckily failed. So, you know.
Yeah.
Prahladh? So
Yes.
you defined HTX as the spectral gap between the down-up and non-lazy up-down walk at each level to be less than lambda. But the
Yes.
distribution was ultimately defined at the level of k-1 and then induced at on the rest of the structure. So is there
Yes.
a way of defining the expansion at one level and then that implying expansion at all the other levels?
Good question. I haven't thought about this. It could be, but I don't know how to. Yeah.
I mean, there should be some sort of relation between this expression at each of the different levels, since they're all derived from just one distribution, right?
Could be. I haven't thought about this. Yeah.
So what's the question again?
No, so here it's defined that for each I up to k-1, m down minus non-lazy m up should be less than lambda. Is it enough to define it at the k-1's level and then that will force it on all the other levels? Because ultimately you just have one distribution and the downward closure of a simplicial complex induces a distribution on the rest.
Yeah, so where is your town? Yeah.
So the answer is actually yes. I mean, if you define it on the top level, in some way indirectly it implies that the same relation will still apply when you look at the upper and lower walks down below.
So what's the relation between this expression on different levels? Is there a constant change, or like if you start at the k-1 level as a difference of lambda, what happens? What is the natural implication on the other levels?
So first of all, as Rick said, you do need to like have some other weak assumption on the simplicial complex for this to work. Generally, the bound gets worse. So if you have a lambda difference in the top level, then it's supposed to get worse. And the way you know to show that this still works is like a bit indirect. So you need to like calculate the constants. But since today we know how to construct these objects for lambda being arbitrarily small, then it's okay to just look at the definition at the top level and then, compensate with a better lambda there to get some bound on the lower level.
I think one answer is lambda is less than 1 over the dimension, or maybe 1 over twice the dimension, then you can go all the way down using a factor 2.
So 1 over 2k?
It's 1 over 2k, if you're k dimension, yeah. Then you can go all the way down paying a factor 2. If it is more, there's nothing else.
Okay, so thank you very much, and we'll break and we reconvene at 11:30. Thanks, Prahladh, for the heroic effort.